In the previous video, we discussed about various types of lithium-ion models available in PyBaMM. In this video, we'll talk about another popular type of battery modeling approach, which is equivalent circuit model. So broadly speaking, ECM models can be classified as resistive models or Thevenin models. Resistive models are the ones which consist of open circuit voltage and internal resistance as the only two electrical components to represent entire dynamics involved in the battery. These are not very accurate models and will probably miss most of the nonlinear transients, but is a good starting point in absence of lot of test data. And these are the easiest ones to be built. The second one is Thevenin model, which comprises of additional RC branches to capture the nonlinear transients, which can be attributed to intercalation, diffusion, slow diffusion process within the lithium-ion battery, etc. So to begin with, let us import PyBaMM, and before we move into exploring the different models, let's first understand what are the different categories of models available within PyBaMM. So within PyBaMM, if we do pybam.models.all, we can get 4 different types. So we have base models, event, full battery models, and submodels. Now within this full battery model, we further get base battery model, equivalent circuit model, lead acid, lithium ion, and sodium ion. So today we are interested in equivalent circuit model, so we can further look into what's there inside it, and we can see that it comprises of ECM model options. These are just options like number of branches, etc., which might be the tuning factors to change the architecture. But on the hindsight, we can only see Thevenin model, and there is no direct option for resistive models. So now let's understand how resistive models actually work, and then we'll build around it using simple empirical relations to recreate a resistive model. So to begin with, resistive models are also known as Rint model. And this section just highlights a pseudocode of what's happening in the background. So as we can see in this image, the open circuit voltage is nothing but R0 plus basically the terminal voltage plus the voltage drop across the internal resistance. So that's the voltage balance equation. OCV equals to V plus I times R0. Now we can rewrite this equation as V equals to OCV minus IR0, and we'll come back to this soon, as OCV and R0 are typically known and I can be derived from the following equation. So we have rewritten in the following format. And our objective is to calculate terminal voltage. Now capacity, let's assume for this study, we'll assume a 2.16 ampere hour cylindrical cell, and its C rate is, let's say, 1. So the current is nothing but capacity times C rate, which is 2.16 amps. Now OCV and R0 typically are a function of SOC and temperature, and it can be either derived from supplier spec sheet or through tests which involve very low C rate, discharge, and charge at different temperatures. Alternatively, GITT test can also be used, where a small pulse is given followed by a long rest period, so that it allows the voltage to stabilize to the respective OCV at the given SOC. So with this, this is what we need to solve in the background. We need to define OCV maps. OCV are not map as a function of SOC and temperature, so it's a lookup map. Once this is defined, we just need to establish a relation for current with respect to capacity and C rate, and we are good to calculate voltage. And this is how we'll basically build around resistive models within PyBaMM, since it's not directly available as an option. So to begin with, we'll import NumPy as NP because we'll be storing all these maps using NumPy. And to begin with, we can define SOC grid. So this will be the discretization of SOC for OCV and R0 map. So we have chosen relatively coarser mesh. It can also be resolved to typically the industry standard is to have it around 1%, but which is 0.01. So we'll end up getting since SOC is 1 to 100, so we'll end up getting around 100, 101 points. Similarly, temperature can be further defined as a grid. We have considered 4 temperatures, but it depends on the end use. So if you plan to use the cell in a wider range of temperature, you can increase or decrease the window and then define the resolution based on how much change do you expect from one temperature to another. So in this case, we have chosen a 10 degree Celsius or Kelvin delta for defining the temperature grid. So once the SOC and temperature grid is defined, SOC grid consists of 11 points, temperature grid consists of 4 points, and then the OCV map is basically 11 cross 4. So each of these data points, each of these row represent one temperature. So this is 283, and each of the values are at different SOC levels. So we end up getting 44 data points for OCV map and 44 data points for R0 map. Again, you can simply use a spec sheet, use some GenAI tools to digitize the data, and then define it in this uniform format. Next, we'll import matplotlib and then try to define a plot. So let's probably run this code to begin with. What's happening here? We are trying to plot this data, the raw data, which is the OCV R0 maps. And we are trying to look at how the contour looks like. So basically we have defined AX1 equals to a figure dot add subplot, and it's a 3D projection, so we'll get a 3D isometric view, and each of these lines basically represent the contours at different temperatures and SOC. So we have defined axis contour 3D, X and Y is SOC and temperature, and we are subtracting 273 to get temperature in degrees Celsius. Then we are feeding in the OCV map. So that's the syntax X, Y, and Z. And then finally, the number of discretization lines that we want for each axis. So the first figure is OCV, and we have 20 lines. Each of these are basically derived from the original data set. And similarly, on the right, you can see the R0 map, which is defined here. And then we are plotting it with a tight layout. So the tight layout will help us plot side by side and have a quick comparison and sanity check of the data set being used. So we can see that OCV is increasing with SOC, and it's more or less constant with temperature. We don't have a temperature variation of OCV, but it depends on chemistry and can vary. Generally, it's more or less in the same range. R0, on the other hand, has significant variation with temperature and SOC, as we can clearly see here in this plot. Now, next step is to interpolate. So since the original data was discrete points, as we solve PyBaMM equation, PyBaMM's, although we might not be using inbuilt model, but still it's a good practice to interpolate so that depending on the time step, we might end up not using or not reaching any of the grid points, but we might want to interpolate in between to find what's the value as a lookup. So we have we're using regular grid interpolator option from this Skype.interpolate library, and we'll do the OCV interp. We'll create a parameter OCV interp and do regular grid interpolator, which basically takes the following arguments. It takes x, y, and then outside bracket the z values. So we have temperature grid, SOC grid, and then finally OCV map. Similarly, we'll do the same for R naught. So this will help us interpolate so that we can easily look up any values and within the data set. Next step, coming back to the original definition. So QAH is 2.16, C rate is 1, current would be 2.16 times 1, which is 2.16 amps. And let's fix the temperature to be 298 Kelvin. Now, another important concept is Coulomb counting. So since we are not using an inbuilt model, we need to also solve for SOC empirically. And the most commonly used or most popular option, which is being used at a initial level of analysis, can be Coulomb counting. There are some advanced options as well, which people use for commercial purpose, like Kalman filters or even hybrid models of voltage and SOC, voltage and Coulomb counting. But for this exercise, let's stick to Coulomb counting. So we have dt equals to 1 second. This can be changed as needed. OCV is OCV 0. We are just initializing the initial values here. So OCV 0 is OCV interp T to 98, comma 1. We are starting with a fully charged cell. So SOC is 1, and then we're taking the value. Similarly, R0 0 initial value is R0 underscore interp, and then we look up with the same inputs. T is initialized to 0, and SOC is initialized as 1. Finally, we'll initialize the voltage as OCV minus I times R naught, both at initial conditions, which are defined here. Now let's enter a while loop where we will keep on appending the values of time, SOC, and voltage, and also do Coulomb counting to update SOC. So while voltage is, and we're taking the last value, -1 represents last value in Python. When the last value of voltage array is greater than 2.5, which means we are trying to restrict it to stay above the lower cutoff voltage limit. And also if the SOC of the last value is greater than 0. So we have both the conditions being satisfied, being considered, and if either of them is kind of reached, we basically end the while loop. So while voltage is greater than 2.5 and SOC is greater than 0, we do the following. We do SOC new equals to last SOC, SOC t minus 1, as you can see in this formula, minus, now here we are using a plus symbol because we are assuming that I is negative while discharging, but the convention here is opposite, so we have a negative sign here. Minus I times dt divided by 3600. That's just added to convert seconds, because dt is in seconds here, 1 second. We're converting it to hours. So we're dividing seconds by 3600 to get hours, and then we have current in amperes, so we finally end up getting ampere hour, and that is divided by the capacity in ampere hour. So we are basically normalizing it and subtracting it from the last SOC. and that is what you can see here. It's I by Q times dt. Then once the SOC is updated, we can look up into the OCV interpolation function. So we do OCV equals to OCV interp T SOC new, and similarly do the same for R0. Update the voltage value with OCV minus I R0 formula. And then finally append to the array T, SOC, and voltage. T is considered to be just a summation of the last time plus the time step. So we assume that we are taking equal time steps, and hence this formula will work here. Finally, we'll compare it with the experimental data. So we have T experiment equals to np dot array, and then we have defined the experimental. Let me quickly run these codes as well. So we have defined experimental temperature here, which we'll compare to. So we have, experimental time, SOC, and voltage. And again, these are defined as discrete points. We have the data for 298 Kelvin at 1C discharge. Then finally, we plot it here using matplotlib. We have covered this previously, so I won't go into the detail of this. You can rewatch my previous video. So this is the final result. Simulation and experimental results overlap nicely for both voltage as well as SOC. So this is how you can model a resistive model within PyBaMM.